Hey. I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh, yeah! Check out my new weapon. Piranha gun! Oh, yes! Fires live piranhas. Ever seen one before? No, you haven't. I invented it. Do you want a demonstration? Oh, ah! Gosh, it's so difficult sometimes to get the line back inside.
Okay, so that clip illustrates vectors. We know now, thanks to Victor, that vectors are a quantity represented by an arrow with both direction and magnitude. Oh yeah, oh yeah. All right. So in all seriousness, though, we can go ahead and represent them with our cool little arrow. So I'm going to have my little vector here. Boop, doo. So there's my vector. So the neat thing about vectors is they're not tied to a specific place. They're just tied to that direction and magnitude. So this vector will simply represent moving over 2 units and up 3 units. It doesn't matter where it is. If it's over here, it basically means, okay, we're moving over 2 up 3. If it's over here, it means we move over 2 up 3. Vectors are usually written with like a letter. Oftentimes it's V, but it could be R or something like that. And then over the top is like this little one-sided arrow type thing. So this could be vector R. And then we know that it goes, in this case, over 2 up 3. But we could have a larger vector too, right? So we could say, okay, here's a vector that goes over 4 up 4, or something like that, right? And then we can come up with a label for this. We can say this is a vector T. So there's vector T. Cool. So vectors are pretty useful. We can basically apply vectors to certain things. I can make a little figure here. In this case, I'm not going to do like a... I'm just going to make a really basic triangle. So here's my triangle. Whoa, that was off. Yeah. Okay, Mr. Peanut Gallery there. Nink. Okay. We'll do a better one. Yep, this is... Hey, you bumped my arm. Okay. So there's my triangle. I'm going to apply one of these vectors. Which one should I apply? Should I apply the red one or the purple one?
Purple.
Okay, so I'll apply the purple vector. So the nice thing about having the whiteboard here is I can just... Stop, please. I can just scoot it over, and it tells me exactly where I want to end up. But we can also just use the distance over. Remember, we decided that this one goes, if we count the units, 1, 2, 3, over 4, and then up 4. 1, 2, 3, 4. So in this case, we go over 4. 1, 2, 3, 4, up 4, 1, 2, 3, 4. That gives us 1 point. If we do the other one, 1, 2, 3, 4, 1, 2, 3, 4, that gives us the other point, and then finally this point. So if we apply one of these vectors to a figure, that gives us a translation, right, where it scoots over and up. That's the reason why we need to cover vectors a little bit more. We can get a little fancier too. Specifically, we can talk about how to label these things. The red one, since it goes over 2 and up 3, we're going to list this as if, for a second, just pretend that it was on the origin here for me for a second. What point does this vector terminate at? Well, it terminates at the point 2, 3. So we would label that red one as 2, 3. And then if we just wrote 2, 3, it would look like the point 2, 3. Right? We don't want the point 2, 3. These parentheses kind of make it look like it's a point we're talking about. We don't want the vector to be represented by a point there. We want to put these little angled brackets in. So this means we're talking about a vector, not a point. And the vector means 2 units to the right and 3 units up. Well, what about if we want to go down or left or something like that? Well, in that case, we would simply use a negative value. So I can write a component form for a vector that's negative. I can say, what about, give me a number, Aaron, a negative number.
Negative 800,000
Right,
million.
we'll try -8. Give me another negative number.
3.
3?
Yeah, 3.
Good job, Ren. Okay. So there's -8, 3. So what would this vector look like? We can draw this one. This vector is at -8, 3. So therefore, the -8's the horizontal component. So we're going to go over 8, 1. We'll start here. We'll go 1, 2, 3, 4, 5, 6, 7, 8. And then down 3. 1, 2, 3. So we go from here to here. And it's super straight and accurate. Good, that's my vector. -8, 3. So you could have vectors in all sorts of direction and all sorts of sizes, and they're pretty cool. We can also add vectors together. Let's go ahead and practice adding vectors here for a second. I could have 2 vectors. I can have, let's say, Renner, stop please. I have a purple vector here, and let's say I have a blue vector that goes like this. It goes like that. Okay. Let's go ahead and write the component forms of these guys out. The component form of this vector is 2, 3. So I'll just go ahead and write it 2, 3. The horizontal change and then the vertical change. The component form of this blue vector is going to be 1, right? 1 to the right and then down 2. So -2. Boys, if you can't sit still, you can leave. Okay, now, as it turns out, I can add these things together. So I'm just going to add them straight together like this. I'll make this cool black vector. What's 2 plus 1? Renner, what's 2 plus 1?
2 plus 1
Is?
1.
What's 2 plus 1?
3.
Okay, Aaron, what's this one? This one's for you. What is 3 plus -2?
1.
Ho ho, very good. All right. So the new vector is going to be 3, 1. So I'm going to go ahead and do this one. 1, 2, 3, 1. The new vector looks something like this. This comes up a lot in physics. So for example, if I were traveling on a car, traveling this direction at this speed, and I threw a ball in this direction at this speed, the actual path of the ball would be like this. Because it's a combination of both what I was doing and what the throw was doing. Similarly, you could talk about like spaceships. If zooming in this direction and then I thrust in this direction, my actual path is this direction. We can show that this is true because if we put these together, it makes a nice little triangle, right? These two vectors added together, the purple one plus the blue one is equal to the black one here. When we add them together. We can also subtract vectors. Vectors. We can do the same thing here. I'll use the purple and then the blue, I guess. So the purple was over 2 up 3. Aaron, please don't. So that's the purple one. And then the blue one we decided was over 1 down 2, like that. Cool. And again, we have our coordinates. So in this case, the coordinate form of the first one we decided was 2, 3. The coordinate form of the second one is 1, -2. And then I could subtract these vectors. Essentially, what I'm doing here is, unlike adding them where I kind of link them end to end, I'm basically putting them point to point like that. I'm going up this vector, and then if I subtract the blue one, I'm going backwards up the blue one here. So we can figure out where that's going to go. What is 2 minus 1, Aaron? Aaron, what's 2 minus 1?
2. 2? Minus 1.
What's 2 minus 1? What's 2 take away 1, Renner?
3.
Oh, good guess. Aaron, what is it?
1.
1, okay. What is 3 minus a negative 2? Tricky one.
1.
No, that's 3 minus regular 2.
Oh.
What's a 3 minus a negative 2?
5.
Whoa, good job. I'm impressed.
Yeah.
When did you learn how to subtract negatives? Crazy little.
I just basically guessed.
Yeah, okay. Okay.
Roasting it.
Yeah, it's kind of like reversing it. Okay, so 1, 5 is our new vector. So let's see if that works out. Again, we'll put these guys end to end here. And then I'll go from here to here. Is this vector 1, 5? Well, it's over 1, up 5. So yeah, that works. Cool. Hey, can we multiply vectors? We can't. We can't multiply 2 vectors together because they just make no sense. You know, a direction times another direction. Nope, doesn't work. But what we can do is we can multiply it by what's called a scalar. I forget the formatting on scalars here, but I'll get that to you. So if I have a vector, we'll do a nice simple one here. This vector is, what is that? That's 1, 2. I can multiply that by a scale factor, right? So I might say, okay, well, I want this vector, but I want it basically 4 times bigger. So if I multiply that by 4, Karen, ready for multiplication?
Mm-hmm.
Okay, what is 1 times 4?
4.
4. What's 2 times 4?
8.
Good job.
Yeah.
Okay, so 4, 8. So my new vector looks like 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. 8 all the way up there. So this is my new vector. So that's my original vector times 4, right? And you can see how I could just, you know, fit 4 of these guys in here. 2, 3, 4. So if I took the original one, made 4 of them end to end, I could do that. So hopefully that figures that one out. And that's it. That's pretty much all we have for vectors. So thanks for watching that. Say goodbye.
Bye. Bye.